Hi Math 213. In this video we're going to be discussing measures of spread, specifically talking about variation and mean, absolute deviation, variance, and standard deviation. So in general we need to include some kind of a measure of spread because usually the mean or median or mode are not enough of a piece of information in order to tell us really what the set of data is doing. So a measure of spread is needed when data are summarized with a single number, such as the mean or the median. And we've already talked about how to discuss the spread of a data set. We've talked about the range, remember, which is just the difference between the maximum and minimum values in the data set, or the upper extreme and lower extreme. We've also talked about making use of the interquartile range, or the IQR, which is, remember, the difference between the third quartile and the first quartile. And we saw this a lot when we were making use of box plots, when we were doing our boxes with our stems on the sides. And we also discovered that we might have to consider outliers when looking at those box plots. So those are definitely good pieces of data to use here, pieces of information to use when discussing the spread of a data set. But I think the best way and the most sophisticated way is to talk about what's called the standard deviation. So we need to do a little bit of development of a couple of concepts before we move into talking about standard deviation, because it's a fairly complicated calculation. So the first one of these deviations or discussions of variance that we're going to talk about is what's called the mean absolute deviation, abbreviated as MAD, of course, like this as an acronym. So the mean absolute deviation, or MAD, makes use of the absolute value to find the distance of each data point from the mean. And this is really one of the most basic ways to measure the spread of the data. And so we have to first figure out just exactly how far away each data point is from the mean. So once we have each of the distances calculated, so figuring out how far each data point is away from the mean, then we take each of those distances and we find the mean of those distances. And this gives us an average distance from the mean. Notice the abuse of the word average here, right? We all have to interpret that this word average here means that they're talking about the mean distance, right? Mean of the distances. Perhaps they don't use the word mean here because we're again using the word mean down here and we don't want it to get confusing. So we figure out what is called the average distance from the mean of the points. So in terms of a formula, it might be better seen as follows. So the steps we're going to produce are the following. Measure the distance from the mean by subtracting the data value minus the mean. The second step is to find the absolute value of each difference. And the third is to sum up those absolute values. This is called the absolute deviation. And the last is to find the mean absolute deviation by dividing by the number of scores, right? Dividing the sum by the number of scores, right? Just finding the specific mean itself by dividing by the number of things you added. So the formula looks something like this. So the x sub 1, x sub 2, x sub n, those are subscripts here. The 1, 2, and n are subscripts. Those are actually your data points. And this means that we have n data points in our set of data. And the x bar, remember, that's notation specifically reserved for the mean of the data set. So in terms of our procedures here, our steps, the first thing to do is to measure the distance from the mean by subtracting the data value minus the mean. So on our next screen here, you see that each one of these individual calculations here is doing what? Finding the distance from the mean of each data point, right? The difference between each data point and the mean. So you take a data point, subtract the mean. Data point, subtract the mean, so on for each of the data points. The next step is to find the absolute value of each difference. And that's what these vertical bars are here. Remember, vertical bars are denoting the absolute value. So in each case, you're finding the absolute value of each of the differences. The third step is to sum up those absolute values. This is called the absolute deviation. So the addition here of all of these absolute values here in the numerator, that specifically is the absolute deviation. Okay, so that's not yet the mean absolute deviation because you haven't yet divided by n. Just the numerator living up here is just the absolute deviation, just adding up all of the absolute values. The last step is to find the mean absolute deviation, which is dividing by the number of scores. And that's the division by n here. So the mean absolute deviation is constructed by this formula. So let's consider an example. So this table shows a set of data along with the computation of the mean absolute deviation. So here are all the test scores. How many test scores do we have? Let's see, we have a 99, 67, 84, 99, and another 67. So it looks like we have 1, 2, 3, 4, 5 test scores. So notice here we're actually computing the mean, x bar, and it actually looks like they forgot a little bit of the notation here, didn't they? And I can actually fix that right now. This is kind of fun. I can actually draw the line where it's supposed to be. There we go. So they're just calculating the mean of the test scores. So what are they doing? Adding up the 5 test scores, dividing by the number of test scores, which is 5. And so we find the mean is 83.2. Now to calculate the mean absolute deviation, what do we do? So first thing is to find the difference between each test score and the mean. So 99 minus 83.2, 67 minus 83.2, and so on and so on, and find the absolute value of the differences. And so here, these numbers here on the right all represent the absolute value of the difference between each data point and the mean. So what do we do with these absolute values over here, these values over here? What do? We add them together, which is the sum of the absolute deviations. That's 64.8. That's if we just said I'm going to add together all of these things, right? If I add together all of these things, that's going to be this 64.8 right here. Once I have that sum of the absolute deviations, I create the mean absolute deviation by dividing by the number of test scores. So I take the 64.8 and I divide by 5 to get 12.96. This is the mean absolute deviation. So in general, the mean absolute deviation, this is kind of like a rough measure of what the average distance that a score is from the mean. And it kind of gives us an idea of how far away from the mean the test scores are. So what the spread looks like, how far on average the data points are away from the mean. And that can be represented visually here by showing, this is a bar graph of the test scores showing where the mean lives here. Yes, so each of the test scores here is represented just by one bar, right? So this is not representing sort of a totaling aspect or anything. So each of the 5 scores represented by the height being the score achieved by the student on the exam, on the test, and the mean is marked with this horizontal pink line here. And what we've done now on this line graph over here is to denote how far away each of the test scores is from the mean. So the mean is sort of this central vertical line here. This is where the mean is. And then each one of these horizontal lines here represents how far away a data point is from that mean. Notice we have 2 scores of 67 it was? Yes, 67. And that's these 2 scores living down here, right? These are the 2 67s. Okay, these are the 2 67s living down here, and remember how far away they were from the mean. They were 16.2 away from the mean. Okay, so again, the mean absolute deviation would do what? Take all of these blue bars and add them up and divide by 5, right? And remember that gave us a 12 and change. So it's telling us on average the test scores are more than 12 points away from the mean. So now we're going to discuss the other 2 types of measures of spread if we're talking about data sets, the ones that are most used in the study of statistics. So the variance and the standard deviation are the 2 commonly used statements of what are called dispersion or measures of spread. So these measures are also based on just how far the scores are in general from the mean. And a nice way to think about the variance specifically, and I'll write you a little note here using my special pointer here, is that the mean of the squared deviations is the variance. Okay, and we've talked about deviations when we were talking about mean average deviation, right? So deviations, remember, just means how far away each data point is from the mean, right? So distance of each data point from the mean. Okay, so really the idea here is that we find the distance of each data point from the mean, that's the deviations. We square that, and then we have to figure out the mean of all of those squared deviations, and that's going to be called the variance. And then once we have the variance, we'll do something funny with it to get the standard deviation. Okay, so let's get back to our little arrow here, and then we'll talk about how we actually compute the variance specifically, right? So this is what we just talked about right now, the mean of the squared deviations. So let's figure out a series of steps we can go through to compute the variance if we have n data points. So the first thing to do is to find the mean of the numbers. Of course, we're going to need this if we're going to find the deviation, right? We want to know how far away each of the points is from the mean, which means we have to know the mean first. Okay, so first find the mean of the numbers. Second thing is to subtract the mean from each number, from each of the data points, right? That's constructing the deviation, right? So if you want to write yourself a little note here, this right here is doing the deviations. Okay. The second thing, once you have those deviations, is to square each of those deviations, each of the differences, right? Square each of the differences that you found in step 2. Once you have the square of each of those, you want to find the sum of those squares, because now we're trying to construct the mean of the squared deviations, right? If we want to write the mean of the squared deviations, then we have to add them all up, finding the sum, so that we can then do what? Divide the sum by n, right? So that's actually finding, remember, the mean. Mean of squared deviations. And notice that at this point, when we say we have the mean, right, we've divided the sum by n, we've now found a mean. What is it, the mean? It's the mean of the squared deviations. Once we've done that, we have constructed what? The variance, right, just as we said on the previous slide. So we now have the variance, and what do we do with the variance to arrive at what's called the standard deviation? The last step here is to find the square root of the variance. The variance is called v, right? So we find the square root of the variance, and that will give us the standard deviation denoted with a small s. Okay, so the first 5 steps here are all about computing the variance v, right? This last step down here is purely for constructing the standard deviation called small s. All right. So in terms of a formula, this looks really scary, I'm sure. This is the formula for the standard deviation, right? S, remember, denotes the standard deviation. Remember the relationship between standard deviation and variance, right? On the previous page with our steps, remember, the first 5 steps were solely for constructing the variance. Once you have the variance, what do you do to get this to get the standard deviation? You find the square root of the variance. So here, when we say S equals the square root of V, that means the standard deviation is the square root of the variance, right? And that's exactly what number 6 is saying, or step number 6, right? And so this inside part here, underneath this big square root symbol here, that's just v, right? Remember that the variance is what? The mean of the squared deviations, right? And if you look at this, that's what this constructs inside of the radical here, inside of the square root. It's a mean because you're doing what? Adding up n things and dividing by n. How do I know there are n things here? Because it's for each of the data points, 1 through n, and it is the sum of the squares of the differences, yes? And this is the variance, which is living inside of the square root here. Okay? Excellent. So let's try an example. So there was a professor, and he gave 2 groups of exams. Exam A had the following grades. There were 3 zeros and 3 hundreds. A pretty big spread, I would say, yes? And exam B had grades of all 50s. Find the following for each of the exams. Okay, let's find the mean for each of the exams. Remember, how do we find the mean? Well, we add up the data points and divide by the number of data points. So in each of these exam groups, there are, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the groups are the same size. They each have 6 exams. And to find the mean, you add up the data points and divide by the number of the exams. So here, in the first one, we are adding 0, 0, 0, 100, 100, 100, and dividing by 6, right? So for exam A, it would be 300 divided by 6, which is 50. And for the exam B, here, the second group, what is the mean going to be? Well, notice they're all the same score, right? So actually, you can do this with, doing arithmetic actually to find the mean, but the calculation should be fairly straightforward since they're all the same value. The mean will just be that value. So for exam A, we have a mean of 50, and exam B, we have a mean of 50. And again, remember the mean is just that balance point that needs to be achieved if you were to make a dot plot of all of the data points here. So the balancing point for this first group of exams would be the number 50 because it's half in the middle. It's right in the middle of all of those. And for exam B, it would be 50 also because the balancing point would be stacked underneath all of those scores of 50 living right there underneath. Okay, so what about the range? The range, remember, for a data set is the upper extreme minus the lower extreme. So for exam A, notice the upper extreme is a score of 100 and the lower extreme is a score of 0. So the range there is 100. And for exam B, the range is what? They're all the same score, which means that the range is 0. There is no difference between the upper and lower extremes. So for exam A, we have a range of 100, and exam B, we have a range of 0. Again, remember these the mean is a measure of central tendency. It's a measure of where the center of the data in general lives. These 2 exams have the same measure of center, right? They're both centered about 50, but their distributions are totally different. The spread is totally different. And so here for parts B and C, we're really starting to talk about spread, right? So this is really where we're starting talking about deviation or spread. And in part A, we're really talking about the center. Okay, so in part C, we're asked to calculate the mean absolute deviation. Okay, now we can go through the complete calculation and practice it, or we can think about this a little bit more intuitively here. Remember that the mean absolute deviation is what? The average of how far apart each of the data points is from the mean. Well, in part A, we found the mean for each of the exams. For A, it was 50. How far apart on average are each of the points in A from the mean of 50? Well, remember that little the little line graph we had with the bars measuring how far away the data points were? If we think about that, each of the data points is 50 away from the mean, isn't it? Yes, 0 is 50 away from the mean. 0 is 50 away, 0 is 50 away, 100 is 50 away, 100 is 50 away. They're all 50 away, which means the mean of those distances is 50 because they're all 50 units away. So for exam A, the mean absolute deviation is going to be 50. And what about for part B? Are the scores at all apart from the mean of 50? No, none of them are any distance away from the mean. They're all exactly the same as the mean. So for exam A, we have a mean absolute deviation of 50, and exam B, we have a mean absolute deviation of 0. Okay, again, that's a measure of the spread. Maybe a little bit more, giving us a little more information than the range is, right? Because it's telling us more about where the data seems to be clustered, right? It's telling us exam B is all clustered exactly at the mean, and exam A has a much greater spread. All right, let's see how the standard deviation would be calculated for each of these exams. Okay, so this means the standard deviation for exam A, that's a little subscript here, right? So this could be written as standard deviation for exam A. And this will be standard deviation for exam B. Okay, so here notice that the standard deviation, remember, says to do what? It says to calculate the difference between the data points and the mean, and since there were 3 scores of 0, that means we have 3 expressions that look like this, yes? And since there were 3 scores of 100, we have 3 expressions that look like this, yes? And so now it says to add up all of those differences here. So we follow order of operations here. We find the difference first and then square it, then multiply by 3. If you don't want to do the multiply by 3, you could have had 3 of these here. You could have had 3 of those, so you would have 0 minus 50 squared plus 0 minus 50 squared plus 0 minus 50 squared plus, and then you would again have 3 of these, right, these squares right there. But they just simplified it to make it a little bit more compact notation. Okay, so we perform the difference, then the squaring action, then the multiply for both of those, add them together, divide by 6, and then take the square root. And once we're done with that, we get a standard deviation of 50. And we do the same thing for the standard deviation for exam B. Now remember, all of the scores were 50, so that means there were 6 of these expressions, right? 6 of these differences here, because each of the scores is 50 and there were 6 of them. So when we compute this, remember 50 minus 50 is 0, so anything we do after that, squaring it, multiplying by 6, dividing by 6, taking the square root, that's still going to return a value of 0. So again, notice this is saying the standard deviation is 50 for exam A and 0 for exam B. Again, the spread for exam B is 0. There is no spread. All right, what about the median for each one? Remember the median, we line them up and choose the middle one. Since there's an even number of scores, we take the mean of the center 2. So let's see, let's go back a second here. So for the first group here, the mean of the center 2, so that's going to be these two. The mean is going to be 50. And for the second group, the mean is going to be the average of these two center ones, which is again 50. So the median for each one is 50. And the interquartile range, remember how we do that? We figure out the first and third quartiles, and then we find the difference. I'll let you practice on that one and confirm that you get the same values here. Just if you don't remember how to do that. Remember, we found the median for each one was a value living right here in the middle, and Q1 and Q3 would then be here. This is Q1, and this would be Q3. Yes, and you find the difference. And then this is Q1, and this is Q3 for the second one, and find the difference. So that's how we're getting here 100 and 0 specifically. Okay, so one application of these standard deviations is what are called normal curves. I didn't assign any homework on this, but at least it's a good idea to discuss it together because you may hear or see these kind of distributions or collections of data. Distribution just means a graphical visualization of the data that you have. So standard deviations are regularly used with what are called normal curves. And a normal curve is a smooth bell-shaped curve that depicts frequency values. So it's a frequency graph. A higher point on the graph means more frequency, means more values. And it means it's distributed symmetrically about the mean, specifically for a normal curve. We want to see a lot of symmetry about the mean. What's unusual about a normal curve is the following. The mean, the median, and the mode all have the same value. And so let me show you what that means. It's going to look, hold on a second, I want to get to the graph. Here we go. So this center point right here, this height, is the mean as well as the median, because notice it's the middle of all of this data here, right? The height, remember, here the height of the graph represents the frequency or number of data points representing that value. And it's also this is also the mode, because this height represents frequency here, that means the most number of data points occur here, right, at this data point, whatever this is. Okay, so if we go back a second, we can notice a couple other things. The curve extends indefinitely in both directions and gets closer and closer to the x-axis but never touches it. And the curve is symmetrical about its center point. Okay, so a normal distribution must be symmetrical, but a curve being symmetrical does not necessarily mean it's normal. It has to have other characteristics as well. Okay, so what's interesting to note about the graph here is that these vertical lines represent standard deviations away from the mean, and the percentages represent the amount of the data that would be, for example, one standard deviation away from the mean. So if we found out, for example, that our standard deviation was, what did we find in the previous example, 50 or 100 or 0 or whatever. Let's say for fun we had another data set and we found out our standard deviation was 5. Then what we could say is, if we go one standard deviation away, or if we go up 5 units here, then we would have 34% of our data points being within one standard deviation, or 5 points away from whatever the mean is. And the same thing below. If you go 5 points down, then you would have 34%, 5 points below the mean. So again, test scores are a perfect example of this. If you had a mean test score of 75, let's say, then you could say 34% of your test scores would be between 75 and 80, and 34% would be between 70 and 75, because the standard deviation was 5, just for example. Okay, and the rest of the percentages here represent more of the test scores being contained between 1 and 2 standard deviations. So for example, if our mean was 75 and our standard deviation was 5, then we know if we go 2 standard deviations, then we have 34 plus 13.5% of our scores being between 75 and, let's see, 2 standard deviations would be 75 to 85, because 2 standard deviations would be 10, right? Okay. So this is just a way for us to sort of talk about how the data is being distributed in a very specific way. Okay, and specifically on a normal curve, 68% of the values lie within one standard deviation of the mean. That's these two percentages here. They're each one away on either side. And 95% are within 2 standard deviations. So that's everything from here to here, right? So if you add up these 4 percentages here, they will add to 95%. And lastly, 99.8% are within 3 standard deviations. So that would be going out 3 standard deviations on either side. Adding up all of these 1, 2, 3, 4, 5, 6 percentages tells you that 99.8% of your data will be within 3 standard deviations of the mean. Okay, and the percentages represent approximations of the total percent of area under the curve, or the amount of the data that would be contained within those standard deviations. For now, this is a decent discussion of measures of variation, or measures of spread, or dispersion, as we like to say. We'll continue this discussion with perhaps an activity in class or any questions you might have.